after you superheat, you sort of let it expand within one stage from 1 to 2. And then instead of going to 4 dash, what you do is you send it to the boiler and reheat again from 2 to 3 and expand in a lower pressure turbine. So now you're reaching 4, right? And the quality at 4 is greater than the quality at 4 dash for sure. Okay, so what you're doing is very simple, right? The only modification that we're having from a regular cycle is that in the regular cycle, you start with the boiler, you go from 6 to 1. Again, you do the same thing here. Okay. Now, once you have reached 1, you have you have 2 turbines. Okay, so it goes to the first turbine, and in the first turbine, it does not expand all the way to condenser pressure, right? It stops at some point, state 2, which is here. Okay, it expands a little, stops at 2. Then at state 2, we again send it through the boiler. We again send it to the boiler and heat it up again, and which is what's called the reheat. Then it's again at a higher temperature, T3, again the superheated vapor region, and then we expand it again. Okay, so this is all what's happening. So you're having expansion of steam within a high pressure stage, then you reheating, again expansion within a low pressure stage. So how did it help? Well, basically it helped us in pushing the thing to the right. Okay, so we were able to push this entire the expansion stage to the right and basically increase the quality at the exit of the turbine, while also increasing the thermal efficiency again, because here again, by doing this reheating, we are again increasing the temperature at which heat is being added. Okay, so this is another way of basically increasing the thermal efficiency. But again, it comes with its own advantages, right? With the advantage that the moisture content is sort of limited. So this is a very simple modification that you need to do. But when you're doing this, you need to make sure that you consider the work done in both turbine stages, the high pressure and the low pressure turbine, as well as consider the heat input in 2 stages, what is from 6 to 1, right, in the main boiler, and then from 2 to 3 in, let's say, the superheater or in the reheat section. Okay, so the efficiency formula changes accordingly, takes care of the work output from both stages of the turbine and the heat input at both places. Of course, again, this is another way where another modification where we are increasing the heat input, but the net work output increases much higher than the amount of heat that you need to add. And that's simply because the thermal efficiency is higher. Okay, and thermal efficiency is higher from the simple aspect that we're able to increase the temperature at which heat is being added. All right, so this is all sort of interrelated. So the question is how efficient it is, right? So when you're talking about having one more turbine, putting all this piping to send it through the reheat section or to the boiler again, there's a lot of cost involved, right? I mean, nothing comes for free. So you have to see if it makes economic sense. Now, when you do a single reheat stage, meaning you have you have 2 stages of turbine, one the regular turbine expansion, and then one more low pressure turbine with a single reheat, meaning that you're sending it just for one reheat. In this modification that we have just discussed here, the efficiency increases by around 4 to 5%. Okay, so this is a reasonably high increase as we have discussed before, and this is very good. It makes economic sense. I mean, the extra cost that you incur in putting one more turbine, putting all the piping, it all makes sense, and you get that money back pretty soon. Now, of course, you don't have to stop at one stage. You could, instead of letting it expand all the way to condenser, you could also sort of send this part again to the boiler, again get it heated up, expand in one more turbine stage. Okay, so you could do this. It would show up here on this on the TS diagram as something of maybe sending again to another stage and then expanding it. This is something you can do, but since all successive expansion stages happen at lower and lower pressures, the increase in efficiency that we are able to achieve, it sort of diminishes. So in the first reheat, which is what we have here, we get 4 to 5%. In the second reheat, we get somewhere around 2%, right? So it is good, but the economics don't pay for it. It does not make sense from an economic point of view. So yes, you can do multiple reheat stages, okay, but the most common design that you'll see across power plants is a single reheat stage. Okay, so and simply because it makes more economic sense. All right, so if let's say the oil prices go up, And if it makes economic sense to add one more turbine blade, one more reheat stage, people will do it. As of now, it does not. And it may not make sense in the future as well, because we have a solid competition to generating electricity from this Rankine cycle. That is, you could, if the oil prices go too high, you could just switch to solar PV and get power from there. So these are the various options available. These are the different, let's say, modifications, rather simple modifications, but modifications that allow us to improve the efficiency and go from 31% to 45%. Okay, which is a huge difference. So all of these are done in together. So you increase the boiler pressure, you decrease the condenser pressure, and you do superheating and you do reheating. All of these combined, they'll push up the efficiency pretty high. All right, any questions here? Okay, so if there are no questions, let's go and talk about the supercritical Rankine cycle. All right, so this is a very special Rankine cycle in the sense that we are able to operate at very high pressures. Okay, so these are pressures which are like uh, more than 200 times the atmospheric pressure, right? So you can imagine it's crazily high. So the thing is, we knew that supercritical Rankine cycle would make sense in terms of the thermal efficiency. Their thermal efficiency would be higher, but it's just that we did not have the materials to allow us to build a supercritical steam turbine. Okay, so a lot of improvements that have happened over the years in terms of the materials, and not just materials, but also the way we manufacture stuff has allowed us to operate at really high pressures. And this is basically what has allowed us to build what are called as a supercritical plants or supercritical reheat power plants. All right, so we don't have a lot of these across the globe because these have started to come up rather recently in large numbers. I would say in the last 20 to 25 years. Although I think the first supercritical plant was built in the US maybe sometime in the 70s or the 80s, right? So it's not a technology which was developed 5 years back. It's been there for some time, but the the cost and the technology that was needed to sort of make it more mainstream, make it more common, has happened over the last, I would say, 20 years. So what exactly is happening in supercritical cycle? So here, the main difference is that steam generation, it occurs at a pressure which is higher than the critical pressure for water. All right. So critical pressure for water, I mean, this is the critical point that I'm showing here in red. The critical pressure for water is 220.6 bar. So that's 220 times the atmospheric pressure, 200 times the atmospheric pressure, to just think about it in broad numbers. And as you can imagine, it's pretty high pressures, right? So the only difference here is that we do the steam, we generate the steam at very high pressures, and therefore it skips the saturation dome. It does not have to go through the saturation dome. So there's no phase change that occurs in the process 6 to 1. It just you keep heating it. It remains hot water, and at some point of time, it changes its phase from liquid uh, to a special phase, right? So, which is neither liquid, neither vapor. It has properties of both. And this is a special region where you have the supercritical region, where you cannot define the phase as liquid or vapor, but it's a combination of both. So essentially, the only difference that you're having here is that we are operating this at very high pressures. Now, again, going back to 1 minus TL by TH, I want you to tell me what exactly is the difference here, or why exactly is the efficiency of a supercritical power plant higher than a typical power plant? I mean, here in terms of the temperature at state 1, we could certainly reach it even at low pressure. So let's say if I'm drawing the other low pressure cycle here, so in green, so I could actually reach this point, let me call it 1 dash, in terms of the temperature, even by superheating it. So why exactly are we more interested in supercritical, or why do we say the supercritical has higher efficiency? The answer is in the TS diagram and in the formula that we have here.
Because TL is less than the red one or the number one.
No, the TLS sort of fixed. The TLS, what's happening here?
Okay, and TH is kind of fixed. Yes.
No, no. TLS fixed. That's the temperature of the condenser. TH is the temperature at which you add heat. So are you saying TH is changing or?
No, no, TH is changing. So
So TH is increasing and that's why we are having high efficiency. Is that what you're saying?
yes, kind of.
Yep. Well, that's all it is, right? That's the simple answer to it. Uh, when you compare the, oh, I shouldn't have erased that. Let me draw it again. When you compare a regular cycle, uh, right? So a regular cycle has to basically, when it's operating at a pressure lower than the critical pressure of water, meaning when it's operating at any pressure lower than 220 bar, when you heat it up, there will be a point where the liquid will get converted to vapor, and it has to go through this phase change process. Okay, so this phase change process is a very it's a process that we don't really like because it's reducing the temperature. I mean, we are adding so much heat, but there is no change on the temperature. The temperature remains constant, right? And so that's not something that is ideal because we want TH to be as high as possible. And TH is not a single number, right? It's sort of an average temperature during the heat addition process. So to avoid or to skip that, to ensure that every joule of heat that we add is resulting in an increase in temperature, the only way to do that is basically to go supercritical, meaning this line, this black line here, shown by the red arrows that I'm drawing right away. So when you go supercritical, you don't have to go through the phase change. So there will be no point where you are actually where you're supplying heat, but no temperature, the temperature is not changing. All right. And the only way to do that is to avoid phase change, nothing else. Because if you have a phase change is always going to happen at a constant temperature. And all the heat that you provide is going to be used up only uh, to change the phase from liquid to vapor. So skip phase change, you're able to increase the temperature much higher, right? And this is a simple reason you're able to increase the average temperature of heat addition and thereby the efficiency. So when you talk about thermal efficiency, these efficiencies are reaching as high as 47%, right? And of course, when you go to very high temperatures, it makes sense to do a reheat as well. You don't want to just expand it all the way down to the below atmospheric pressure from a pressure which is so high, right? So you have space for two stages of reheat also if you like, because the pressure that we're dealing here is pretty high. So yes, usual power plant you can achieve around 45%. Supercritical you can go pretty high. 47 is what is already there in the market.